All right, let's get started. Is there a garbage can in here?
Nope. No, no.
That is pretty terrible. It's no wonder all these markers are piling up. All right, I'll just make a pile of them as we go through and figure out which ones actually work. All right, so first lecture today, starting with geometry. What is geometry? Strictly speaking, if you just look at etymology, it is earth study, or earth measurement, the measurement of the earth. Practice has started largely with the Egyptians, some of the ancient Babylons too. But it started as a purely empirical science. You know what empirical means?
Basically, the numbers, right?
No, empirical is you go out there and you actually look at it. You go empirically look at things.
So it's like a
So someone told you there's no such thing as a number 2. Show me the number 2. Number 2, that's not a physical object. There's no empirical observation number 2. So it's something that you go out there and they see out in the real world. And they kind of know some general patterns, right? They didn't prove, the ancient Egyptians didn't prove that the angle sum of any triangle is 180 degrees. But they started to notice some weird patterns. You know, they tried to measure and they said, this one comes out to about 180 degrees. This one comes out to about 180 degrees. Is it exact? They didn't know. But they knew it was close to 180 degrees. They knew that if you had a triangle and you called made one side 3 units long, whatever they used for their units, meters long, and you made another one 4 meters long, and this one 5 meters long, then they knew that this was close to a right angle. Was it exactly a right angle? They didn't know. Or they knew it was close enough. So they started to make all these empirical observations and kind of collect together all these empirical observations. It's Thales of Greece that starts actually proving things. So it's the Greeks that start this whole method of actually proving. The Egyptians, they noticed some empirical patterns. The Greeks said, that's interesting. But is that always the case? Or is it exact? Or is it just close? Is it just we happen to keep picking triangles that keeps almost adding up to 180 degrees every time? So that's where the ancient Greeks come in. So it starts with Thales. That's where proving starts. That's where geometry as a proper study starts. So ancient Egyptians and Babylons doing this for a long time. Thales, he's around the year 600 BC. Then we have Pythagoras. We know what he's famous for. The Pythagorean theorem. So he set up a whole school that started actually formally studying this stuff. And then you get all the point to Plato setting up his academy. The first higher level institution of education ever set up in history, the academy. And Plato had one requirement if you were going to come to the school. You had to know geometry. He was inscribed above the door, let none ignorant of geometry enter here. He outlines what he thinks is a proper way that you should go about studying. He says first arithmetic, then geometry, then solid geometry, then astronomy, music, the dialectic, for whatever reason. This is what he would have called his philosophy. But the point is, this was a massive cornerstone to getting in. The point of studying geometry was to teach you how to apply logic and deductively reason. He wanted you competent operating in axiomatic systems. That was the point. Then you have Aristotle, the father of logic and science. He comes afterwards. And Aristotle is the one who really sets up the logical foundations of geometry. So Plato starts noticing that in geometry, when we talk about geometry proper, we can start setting up these proofs, and he starts making it systematic. So he started proving some things, It's Plato's academy that they really start bringing these things together and noticing, with this proof you can prove this proof, you can prove this proof. And with this proof you can prove this, you can prove this. Aristotle's the one that comes along, and he sets up the foundations of logic. He says it's actually the rules of logic that we're applying over and over again. It's understanding of logic that you're using to develop these proofs of geometry. So Aristotle's the one who largely gives it its foundations.
So he starts like showing people that all of this is based off logic, right? Pretty much.
Yes. So he's the one that formalizes the rules of logic. He says this thinking that you keep doing in these proofs over and over again, the way that you keep arguing these things, you're using what we're going to call logic. And so he's the first one that explicitly sets up these rules, exactly what logic is, which gives geometry its foundations. And then finally you get to Euclid. Euclid, often called the father of geometry. So what did Euclid do? Euclid wrote a series of books called the Elements, or 13 of them. But he starts with just 5 postulates. 5 geometric postulates. And he shows how using logic, we can start with these 5 postulates when we start our field geometry and start using them to prove everything else. And so he made the entire body of knowledge all reducible to these 5 axioms, applying Aristotle's logic to those axioms. And that's what the field has been ever since. It would be perfectly valid for us to go and use Euclid's Elements as a textbook for this class. We pick one that we think is a little bit better, but this is far better than the majority of textbooks used today, the textbook that he used. Now think how amazing that is. If I were to go get a biology textbook from 2,000 years ago, how good would it be?
It'd be hard to understand.
It would be garbage. Most of the stuff in there would have been considered wrong now. Go get a biology textbook from a couple hundred years ago. Go get a chemistry textbook from a couple hundred years ago. Go get a physics textbook from a couple hundred years ago. Wrong, 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 wrong. Not a single thing wrong. Still a perfect textbook. You can still use it today. Nothing wrong with it. That's the difference between the sciences and a field like geometry, the maths. When you prove it, you show it's impossible for it to be false. The scientists are over there, they're using empirical observation. They're kind of guessing, they're measuring, they're guessing. And so they're going to be right, they're going to be wrong. They're going to find out they're not quite right the vast, vast, vast majority of the time. This over here, perfect. To the extent that we have perfect.
With the technology he had, it's pretty much perfect.
You don't need technology to do the mathematics. You just need logic. You start with these postulates, and applying the rules of logic, you can perfectly determine what we can conclude from those things. You can perfectly show that every time that if all men are mortal and if Socrates is a man, then Socrates is mortal. You know that's true. It's not dependent on how cool of a laser measuring device you have. No way dependent upon that. And so that argument is just as good now as it was 2,000 years ago. So he's the one that sets it up, and Euclidean geometry becomes kind of the standard that every other field is trying to achieve when it's trying to become a systematic field. Like when physics eventually comes along, or chemistry, any other field of study, they try to develop it the exact same way that Euclid developed geometry. It becomes a prototype for how people try to develop fields of knowledge. One of the reasons it's been at the heart of education literally since academy. And so you jump forward in history and you would have studied what were called the liberal arts. If I was teaching you 600 years ago, you would have first studied your basics, the trivium, which would have been logic, grammar, and rhetoric, and then the quadrivium for quad and tri, 3 and 4, which would have been arithmetic, geometry, music, and astronomy. This would have been what constituted your basic education. Again, you notice that logic, foundational, and after logic, we can go to grammar.
What is rhetoric?
Rhetoric is how to convince people of something. So when I construct an argument, when I limit myself, you use logic in rhetoric. So if I were to convince you of some conclusion, one way I could do it is I could flat out show you the logic of it. That's one way. Another way I could do it is I can make an appeal from authority. I say, such and such is the case. You say, how do you know? I say, trust me, I'm a doctor. It's an argument from authority. That has nothing to do with logic. There's no reason for you to find that convincing. That's a rhetorical argument. Or I can make an argument from emotional appeal. I say, such and such is the case. You say, I'm not sure about that. Only an evil person would think that. You must be bad, because you think different from me. There's nothing logical about that, but it's a rhetorical way to argue. So, rhetoric, studying how to construct convincing arguments. Obviously, you know grammar and logic. So, foundation for what was the standard, what was called a liberal education. You know why it was called a liberal education?
It's free.
Free? No, it wasn't free. Nothing's ever free.
Anyone could learn it, right?
It was the education proper of a freeman. If you were going to function as a freeman in society, you better know these things. It's not that society is responsible for making sure you know it. It's that you're responsible for making sure you know it before you function in society. It's your responsibility as a freeman. Right. Well, that's why it's called the liberal arts. Now, for some reason unknown to mankind, logic was removed from standard education around the year 1900. Well, there are reasons. They're terrible reasons, but that would be a lecture in and of itself, a lot of philosophy and history. And so, logic is now kind of to math what grammar is to literature.
You have to understand where you move on.
Right. A lot of people think that logic is somehow a part of math. They're two completely different fields. You use logic to develop your fields of mathematics. Like you use grammar in literature. So most people, for whatever reason, there's a reason that most people think logic is somehow part of geometry and they're somehow welded together. The reason is because to do geometry, you need logic. You haven't had it, so geometry teachers have had to give you a quick crash course on logic before they can start geometry. So the fields don't really have anything to do with each other. It's just you have to know the logic before you can move on to geometry. So that's why it's now given as a little crash course at the start of each of your geometry classes. So that's how it came to operate the field it does today. Okay. So we already talked about this a little bit last time. Different types of reasoning. When you give your reasoning for something, you explain how it is that you know something. And I briefly explained to you that, roughly speaking, there's three types of reasoning. There's deductive, inductive, and abductive. Our standard argument for deductive reasoning was, if all men are mortal, and if Socrates is a man, then Socrates is mortal. If these two things are true, then this is true. These two things imply this. And it's the whole thing taken together that's true. We never said all men are mortal. We never said Socrates is man. We never said Socrates is mortal. We said if these two things are true, then this is true. That whole statement written out, that's what we're calling true. That if this, then this, that whole statement is what's true. And then inductive reasoning, what was inductive reasoning?
Like just something that seems like
it always
happens over and over again.
It always happens.
Perfect.
It must happen always.
Inductive reasoning is the reasoning of it's always happened, so it will happen that way again. Inductive reasoning, we take a bunch of particulars and create a generalization. So we generalize a bunch of particular events. Abductive reasoning is the reverse of inductive reasoning. Abductive reasoning, we use all our generalizations to reconstruct one particular event.
What would make sense, right?
Yeah, it's an argument to the best explanation. Like filling a drop of liquid on my hand on a cloudy day. One of my generalizations is, I need clouds for there to be rain. So I use all my generalizations that I know to try and reconstruct what's going on in this particular event.
Doesn't mean it's true.
No. This is fallible. This is fallible. This is a sure thing. Okay. So now let's jump into what's logic. Why I learned geometry? We'll get past that. We talked about that in the intro class. So now we'll start logic. In logic, we're only allowed to use deductive reasoning. In all of logic and mathematics, it's only deductive. There's no inductive, there's no abductive. There's no, oh, well, you get the pattern. No, you got to prove it. You got to show it. The same way you know that if all men are mortal, and if Socrates is a man, then Socrates is mortal. So, logic, we have propositional logic. Then we have first order predicate logic. I'm just going to call it predicate logic. And then we have logic with, we'll introduce identity. And then these three things together, we loosely call logic. And this is what we mean by logic, the branch of these three things together. So we'll start with propositional logic, and then we'll add on predicate logic, and then we'll add on the law of identity, and that will complete our whole study of logic. So starting with propositional logic, if you want to understand propositional logic, first and foremost, you have to understand this thing called a proposition. Our author uses the word statement. Proposition, statement mean the same thing. I may accidentally say proposition all the time because that's more common language. This is an old textbook. He's going to use statement. So proposition, statement, one and the same thing. What is a proposition or statement? A statement. A statement is a sentence that is either true or false, but not both. A statement is a sentence that is either true or false, but not both. Just for the sake of me not lying to you, you can ignore this right after I say it. Every statement is a proposition. Not every proposition is a statement. What's a proposition? It's something that's either true or false or not both. A statement is a sentence that's either true or false but not both. But you can pretty much think about them being the same. Okay, so we got a statement. First definition. What's a statement?
A sentence that
it's true or false but not both. We can either call it true or we can call it false. One and only one of those.
Right.
All right. Notation. We typically use Greek letters like alpha and beta to represent statements. So if in a vacuum I'm talking on the board and I say, let's look at alpha implies beta, then you instantly know, oh, that's a statement, that's a statement. Okay, so that's how we'll represent statements, is with 3 players. Example, which of the following are statements? Go back home. True. No, it's false. No, it's not a statement.
Yeah, it's a command. It's not a statement.
Not a statement. 2 times 2 equals 5. False. So it's not a statement.
No, that is a
It could be true
statement.
or false.
It's false.
Oh, it's a false statement. Oh, okay. So that is a statement. 2 times 2 equals 4. True. So that's a true statement.
How can you prove that?
We'll worry about that later. First, let's get comfortable with logic. Proofs are a long ways away. New York is a suburb of Los Angeles.
False.
False. So not a statement.
No, it's a statement.
Oh, it's a false statement. Okay. Thursday up tar paper.
Not a statement.
Not a statement. The silliness of speedily.
Not a statement.
Not a statement. I am the most beautiful girl in town.
It's either true or
False.
false statement.
The false statement? Wow, rude. But a statement nonetheless.
Right.
X plus 2 equals 5.
False or true statement. It's still a
Is it
statement.
true?
You don't know.
Can be.
Is it false?
It's a true or
You don't
false.
know.
This is a gotcha. This is what we mean by a predicate. You need to determine what X is before you can call this true or false.
Right, but it's still a statement.
So that's not
No.
true, because it can't be both.
It's not true, and it's not false.
So you know what X is.
Right. If X is 2, suddenly it's false. If X is 3, suddenly it's true.
Right,
We don't know what X is.
Right. So how is it not a statement though?
It has what we call a variable.
Right.
And the variable could in one case make it true, and in another case make it false.
Right, either way, it's a statement. Well, at the same time, it's true and false.
Is it true and false?
Yes, it could be. Yeah. Right. It could be, that's why it's not a statement.
Okay, it could be.
Because
So,
X is 2 numbers.
a
Right.
predicate,
So it's true and
we'll get more into predicates. Predicates, I'll tell you what they are right now, big boy language. A predicate is a proposition value function. You give it a term and it spits out a proposition. You give it a term and it spits out true or false. This is a predicate. You give it an X and it spits out true or false. If you give it 5, it spits out false. If you give it 3, it spits out true. So this is what we mean by predicate. So gotcha then. It takes a variable, it's not a proposition.
So a predicate wouldn't be a statement, right?
A predicate is not a statement. 2 different things. So first we're in propositional logic or statement logic.
Right.
Studying propositions. This is not propositions. It's predicate. We'll get more on predicates later, but just got you there. If it takes a variable, it's not a statement. Okay, now we have sentential connectives. Sentential connectives. These are the terms or phrases that can be connected onto a sentence in any meaningful way. I can take some sentence and I can add on to the sentence and make it bigger.
Okay.
I can take the sky's blue and I can add on to it Frank thinks that.
And that's a...
And so we get Frank thinks that the sky is blue. Frank thinks that is a sentential connective.
Okay.
I can take or. I can take I'm holding a marker or the sky is blue. I can or those 2 together. I can have 2 statements or them together get a new statement. Or is a sentential connective. Anything you can add on to a sentence in any meaningful way. Examples of things we can add on to statements. We can add not onto a statement. We can add and onto a statement. Or Jack believes it is probably the case that if something, then something, alpha, if and only if, beta, etc. These are all examples of sentential connectives. There's infinitely many sentential connectives we can write out. We're going to be interested in a very small subset of sentential connectives. But let's get comfortable with them for a second. Let alpha be the sky is green, and let beta be 2 plus 2 is 4, and consider each of the following. The sky is green and 2 plus 2 equals 4. Still makes perfect sense, right?
Makes perfect sense, but it's not a statement.
So and is a sentential connective.
So with those centennial,
Sentential connectives.
those, can you just take them out when you're trying to see if they're true or false?
Some sentential connectives, when you apply them to statements, the result is still going to be a statement. So notice if alpha were true or false and beta is true or false, then now this whole thing is also a statement.
Right.
And so I can ask you true or false. The sky is green and 2 plus 2 equals 4. True or false?
That's false.
False.
Because
Wonderful.
the sky is not green.
Let's keep going. The sky is green or 2 plus 2 is equal to false.
That's a predicate.
The sky is green or 2 plus 2 is equal to 4. No variables in there. Not a predicate.
It's-
Is that true?
Yeah.
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 Okay, so it's a statement. If the sky is green, then 2 plus 2 is equal to 4.
False.
That's false. Maybe. We'll come back to that later. But you know it's got to be true or false. It's a statement. Jack believes the sky is green. True or false?
You don't know. Predicate.
It's not a predicate because there's no variable there.
It's true or false.
But Jack believes is not what we call a truth functional sentential connector. So you had something that you knew that was false. Adding on Jack believes makes that we don't know anymore if it's true or false. But it's still a statement. It's still a statement though. We just don't know which it is.
What if he believes the sky is green, but then the sky is not green?
We're going to assume that Jack is a sane human being and is incapable of believing in contradiction. All right. And then it is probably the case that beta. If I know beta is true, do I know it's probably the case that beta is true? Really?
No, you know it is.
If beta is true, do I know it is probably the case that beta is true?
No. You know what it is.
We know it is true, but that doesn't mean it was probable. What if beta was you won the lottery? Let's say you just won the lottery. Okay, you won the lottery. That's a true statement. Is it probable? Is it, oh, probably the case. I meant, is it probable? Not probably. Oh well. So, sentential connectives, we can add on a bunch of different sentential connectives. We're not interested in all these different sentential connectives we can add on to statements. We're only interested in what we call truth functional sentential connectives. Truth functional sentential connectives are sentential connectives where, if I know the truth or falsity of the component statements, I can figure out if the entire statement is true or false. So the first sentential connective we're interested in is conjunction. So we can construct new statements by combining existing statements. I can take New York as a suburb of Los Angeles. That's a statement we already saw. I can take I am the most beautiful girl in town. That's a statement. And I can and them together. Right?
You know it's not true.
And we call that the conjunction of those two statements. Right? So, second definition. So your first definition was definition of statement. The sentence inside the true or false not bold. Second definition, conjunction. Conjunction. If alpha and beta are statements, the statement alpha and beta is called the conjunction of alpha and beta. Pretty straightforward? Okay. Now there's a little bit of a problem with that definition. I said if alpha and beta are statements, the statement alpha and beta is called the conjunction of alpha and beta. How do I know that this right here is a statement?
No.
I know alpha is true or false. I know beta is true or false. How do I know that if I and them together, I still get something that's true or false?
No. Yeah, you can.
We do, but we need to come up with a definition of how we know these things. So we're going to create what we call our first truth table. We're going to prove that and is truth functional. That no matter what alpha and beta are, we can always determine if alpha and beta is true or false. So setting up our truth table, alpha is some statement and beta is some statement. We have no clue which statements they are, we just know that they are statements. What are all the possible combinations for alpha and beta? It's possible that alpha is a true statement and beta is a true statement.
Be false true.
It's possible that alpha is true and beta is false. It's possible that alpha is false and beta is true. And it's possible that they're both false. Those are all the possible combinations for the statements alpha and beta. If I know alpha and beta are both statements, here's all the possible combinations here. So now we're going to look at alpha and beta. You're going to get used to this notation. But there's our notation for how we write and. Notation. We write alpha and beta as alpha and beta. Okay. So here's alpha and beta. If alpha is true and beta is true, then the statement alpha and beta is true. Let's set up examples. We'll make alpha each time Donnie's holding a black marker, and beta each time Donnie's holding a green marker. Set up the case. Alpha is true, beta is true. Is it true that I'm holding a black marker and it's true that I'm holding a green marker?
Yes.
Yes. All right. So I'll make alpha true, beta false. Is it true that I'm holding a black marker and I'm holding a green marker?
No.
No, so it's false. And if I was just holding the green marker,
False.
it'd also be false. But as long as I'm not holding any marker, we're good, right?
No. False.
It's false. Right. Still false. So there's our definition for what we mean by alpha and beta. We mean, thank you. We mean true if alpha and beta are both true. Otherwise, we mean false. Okay, so it is a statement because no matter what alpha and beta are, it either came out true or false. So not only is and a sentential connective, it's a truth functional sentential connective. We could still determine the truth or falsity of the resulting sentence by looking at the truth or falsity of its component sentences. Let's go back to Jack believes. So we have alpha here. Alpha by itself can either be true or false, right? I'm going to make up some symbol, and this is the Jack believes symbol. All right, there's the Jack believes symbol. Jack believes alpha. If alpha is true, is it true that Jack believes alpha?
No, you don't know.
No, it doesn't.
No. You don't know.
You
what
can't
Jack
determine
believes.
it. So Jack believes is not a truth functional sentential connective.
Right, you don't know what he believes.
Right, because you don't know what he believes. So we can't do an analysis of that truth functional or of that sentential connective. We can't determine if the resulting statement is true or false just by looking at its component statements, truth or falsity. So Jack believes is not truth functional and is truth functional.
Donnie believes, and we can ask you to believe it.
You can ask me if I believe it, I could be lying to you. How do you know I'm telling you the truth?
Right. Don't know for sure.
You don't know for sure. So in logic, we are only interested in those completely unambiguous parts of language where we can know for sure exactly what's being said. It's taking all language and siphoning it down to its most pure form. The stuff that communicates completely, unequivocally, unambiguously, tells you exactly what we mean. So let's move on to, let's stick with this. So and we accept in logic, and we use and in logic. We did that. What about another conjunction that you've heard about, like the word but? Well, let's think about this for a second. Why don't we use, I'm going to tell you ahead of time, we use and in logic, and we don't use the word but. But kind of works the same way as and, right? So let's combine it and give you an example of why we don't. So some girl tells you, I love you and I love your brother. What is she saying? It's pretty clear. She's saying I love you is true, and she's saying I love your brother is true. That's exactly what she's saying.
Which we can't really know for sure if it's true, but what?
The point is, the way that and is functioning here is completely unambiguous. You know exactly what she's saying. Maybe she's lying, maybe she's telling the truth, but you know exactly what she's saying. She's saying this is true and this is true. That's exactly what she's saying. Let's switch out and with but. I love you, but I love your brother. Are these two statements saying the same thing? No, they're saying something very different. But think about it. She says, I love you, but I love your brother. Is she saying that she loves you?
Yes.
Yeah. Is she saying that she loves your brother?
Yeah.
Yeah. So in a sense, she's saying this is true and this is true.
Right.
And she's saying something else on top of that. Something subtle. Somehow these are connected. And you can't make it explicit what exactly she's saying.
Right.
There's no rigorous definition for this word but like there is this word and. Doesn't exist. So it's an equivocal term. We don't know exactly what it means. There's a little bit of ambiguity. So when we're doing logic, and is a much better word than but. If you're writing a poem, but is a much better word than and. Because in a poem, you intentionally introduce ambiguity. That's part of literature.
With but, is it saying that both can't be true? Or
No. But says, if you want to just look at the logic of it, but functions the exact same way as and.
but it means something different. It means something.
But it means something different. It means this is true and this is true, and there's some subtle connection between these two things.
Right.
And somehow they're interfering with each other.
Right.
And you can't make perfectly explicit what that is. So we like the word and for logic. We don't like the word but. We like the word but for writing poems. We like it for literature.
Right.
All right. So in logic, we are only interested in the univocal parts of language, as opposed to equivocal. Univocal, uni, one interpretation, one meaning.
Equivocal, two.
Equivocal, many. But in short, ambiguous. All right, so we're only interested in truth, functional, sentential connectives. Those are the sentential connectives where the truth or falsity of the resulting statement can be completely determined by the truth or falsity of the component statements. Make sense?
Yeah.
When we had alpha and beta, you can determine if this whole statement is true if I tell you the truth or falsity of alpha and beta.
Right. Yeah.
If I tell you, I don't want to. Jack believes alpha, and alpha is true. Is Jack believes alpha true?
No.
You don't know.
Yeah, you don't know.
Okay, so here is a resulting statements. Alpha is a component statement in this. Alpha and beta are the component statements in this. Let's read it one more time. Sentential connectives, where the truth or falsity of the resulting statement, the truth or falsity of the whole statement, can be completely determined from the truth or falsity of the component statements. So if I know the truth or falsity of the component statement, I can do it for the whole statement. If I know it for the component statement, I can do it for the whole statement. In this case, I can. In this case, I cannot.
Okay.
Truth functional, not truth functional.
Because you don't know both components, correct? Are true
Because
or
even
false.
when you know the truth or falsity of its components, you still can't determine the truth or falsity of the whole sentence.
Because you don't know the full truth and falsity of one component, right? Because of Jack.
This only has one component and one truth functional connected. The one component is the sky's blue.
Okay.
This is just Jack believes. That's not a component statement because that's not a statement. Jack believes is not a statement. It's a sentential connective. It is not a truth functional sentential connective because when we add it on to statements, the result is not something we can determine the truth or falsity of. So it's not truth functional. So we're only interested in those truth functional sentential connectives. The things we can add on to statements, and the result are statements that we can determine if they're true or false by knowing if the component statements were true or false. Let's keep going. Example. Let alpha and beta be two statements. Which connectives are truth functional? Jack believes alpha. If alpha is true, Jack believes alpha is, we don't know.
Yeah.
So not truth functional. Let's try this one. Let's say that alpha is true, then it is not true that alpha
That's false.
is false.
That's still a statement.
What if alpha is false? If alpha is false, it is not true that alpha is true. So this, it is not true that, is a truth functional sentential connective. And we'll encode that with just the word not later on. But there's one that's truth functional. If you know alpha and beta, is alpha and beta something you can determine the truth or falsity of?
If you know alpha is true and beta.
Yeah, sorry. If you know alpha, you also know beta. Can you determine alpha and beta?
Yes.
Yes. So it is truth functional. And here's where I had probable. If you know beta, can you determine it is probable that beta?
That's not.
That's not. Yeah.
No, because it can't be.
No, you can't determine if it's true or false. If you just know beta. Perfect. So not truth functional. So no, yes, yes, no. Right? Okay. So if it's truth functional, we should be able to construct a truth table for it. Basic test. If it's truth functional, we should be able to construct a truth table for it. To give it a precise definition. All right, so let's move on to our second truth functional sentential connective. We call it the disjunction. So if alpha and beta are statements, the statement alpha or beta is called the disjunction of alpha and beta. It is false if both alpha and beta are false, otherwise it is true. Notation, we write alpha or beta as alpha or beta. And was pointing up, or is pointing down. Same symbol. Now, we have a small problem because logic is something that exists in every single language. All these things exist in every language. We're using English. Unfortunately, in English, we use this word or in two different ways. We use it in what we call the inclusive or and the exclusive or. Let me give you an example. I tell you that you must take calculus or physics to apply for my class. Is it okay if you take both calculus and physics? Can you still apply for my class?
Yeah.
Yes. On the other hand, you go to a restaurant, you're talking to the waiter, you place your order, and he says, that order comes with a side of salad or soup. You say both.
That's how it works.
It's not how it works. You meant that in the exclusive or, one or the other, not necessarily both. In logic, we always mean inclusive or. We always mean this one up here. So we always mean alpha or beta to be true if both of them are true.
Even if
Yes. So here's what we mean by or in logic. We have a notion of exclusive or. We hardly ever use it. The symbol for that, if you care, looks like that, but it's not one we use very often. It's perfectly fine. It's truth functional. We could incorporate it in our logic. We just don't really need that.
That's the symbol for exclusive or inclusive.
That's a symbol for exclusive OR, the one we'll never use. Inclusive OR is that one. That's one we'll always use. So exclusive OR, it's a perfectly fine OR. We could have used logic using that instead of the inclusive OR. Would have been perfectly fine. We choose the inclusive OR. So that's one we're going to use. All right. Oh, I wrote for you right there. If we want to use the exclusive OR, if you're bound and determined to use it, you want to use it in one of your proofs, that's fine, you can. We just typically write it as alpha XOR beta. XOR meaning exclusive OR. And then the OR symbol is the same except for with a line in the middle. So perfectly fine symbol, but you'll hardly ever see it. All right, next one. Negation. If alpha is a statement, the statement alpha is false is called the negation of alpha. We also just say not alpha. That's another way we say alpha is false, not alpha. Or another way you can say it in English is, it is not the case that alpha. Those are all logically equivalent. They're all saying not alpha. Notation, we write not alpha as not alpha. Oh, we didn't do the truth table for OR. Let's do a truth table for OR really quick. Make sure we're all on the same page. And then we'll move back on to not. All right, so I have alpha and beta. What are all the possible combinations here? We can have true, true. We can have true, false. We can have false, true. We can have false, false. All right. If alpha is true and beta is true, then alpha or beta is true. Is that the case is here? Black marker, green marker. If I'm holding both, is it true that I'm holding a black marker or I'm holding a green marker?
Yes.
Yes, wonderful. Let's go to this case. I'm holding a black marker or I'm holding a green marker?
Yes. Yes.
Yes. Let's go to the next case. I'm holding a black marker or I'm holding a green marker?
Yes. Yes.
Wonderful. And then last case. I'm holding a black marker or I'm holding a green marker? No, that's not true. So that one's false. Wonderful. So that's OR. Now let's move on to not. So when we negate, we just negate one statement. So we have alpha, and we're going to look at not alpha. And if alpha is true, then not alpha is
Not true. It's false.
false. And you just stumbled on something very subtle that is going to confuse you, even though it sounds stupid obvious. Not true is the same thing as false, and not false is the same thing as true. If alpha is true, or if alpha is false, not alpha is true. Not false is true, and not true is false. Sounds obvious, yeah.
But what if that's not like?
If alpha is a statement, means it's true or false.
Yeah.
Then not alpha is going to be false or true.
Well, what if you get a statement where alpha is false, but not alpha can be false too? What if you get a statement like that?
It's not a statement. If your statement is false, then not alpha has to be true.
The opposite.
The sky is green. No, it's not green.
No, it's true. It has to be.
The sky is green. The sky is not green.
Oh, okay.
One and only one of those can be true. One and only one of those can be false. And in fact, if alpha is any statement, one and only one of them has to be true, and the other one has to be false. So we call these two statements alpha and not alpha. They are contradicting statements. They are the contradiction of each other. So alpha, it's got the simplest truth table here, but it's actually one of the hardest ones to grasp and understand. You might think I'm lying a little bit, but you won't here in a second.
Some of the stupidest things that hit you in the face.
All right. So not alpha is the contradiction of alpha. If alpha is true, not alpha has to be false. If not alpha is true, alpha has to be false. If not alpha is true, alpha is false. If alpha is true, not alpha is false.
Okay. Yeah.
Maybe I said the same thing both times. Sorry if I did. I meant to switch them both ways. All right. So we always either know that alpha is true or not alpha is true. Oh, sorry. We either know that alpha is true and not alpha is false, or that alpha is false and not alpha is true. It always has to be one of those two cases. They can never be the same, but you'll see the subtleties I'm trying to get at here. So Question, which of these following statements are contradictions? Sorry, I used negations here. Negations were not even. Which of the following are negations of all swans are white? So here's our alpha.
What about contradictions? Right? Some swans are black is obviously not alpha.
So some swans are black is obviously could work as a not alpha, right?
Right. Same with the next.
Perfect. Now let's stop.
Oh.
Thinking too far ahead. You already fell for the trap. I told you this one's the hardest. And you'll fall for this trap a lot. All swans are white is either true or false, right?
Yes.
If it's true, then this one better be false. If this one's true, then this one better be false if they're contradictions of each other.
Right. Exactly.
Let's see if that's the case. All swans are white. Some swans are black. Let's imagine that we live in a universe of yellow swans. Is it true that all swans are white?
No.
No, so then some of them are black.
No.
No!
No.
So this is not the negation of this. If this is alpha, this is not alpha. This is just another statement. We call these two statements contrary statements. Contrary statements are statements that can't both be true, but they're not the negation of each other.
Okay.
We're looking for the negation of alpha.
So you have to make sure alpha is true.
If alpha is true, not alpha better be false. And if not alpha is true, then alpha better be false.
Okay.
It's subtle. So let's move on to the next one. At least one swan is black. Okay. There's our negation, right? It's either the case that all swans are white or at least one swan is black.
Well, let's take the yellow swans.
Let's take the
That
yellow
can be
swans.
true.
All swans are yellow. Let's imagine we live in that universe. Are all swans white? No, so at least one swan is black.
No.
No! So these are not contradictions of each other. This is not the negation of this. Let's go back to simple negation.
But
The sky's blue and the sky's not blue. One of those has to be true, one of them has to be false. There's no way around it. If the sky's blue is true, then the sky's not blue is false. If the sky's blue is false, then the sky's not blue is true.
okay.
You can put the answer to every problem on your algebra test. The answer is 4 or not 4. It's 4 or it's not 4. That's the answer.
Okay.
Yeah! Because it has to be one of the two, because those are negations of each other.
There's no.
Either the answer is 4 or the answer is not 4. They're negations of each other. When you have a negation, one always and forever has to be true, and the other always and forever has to be false. Alright, so this is not the negation of this. This is not the negation of this. I want to give you 3 in a row that aren't the negation, so this must be the negation of this, right? Not good reasoning. Let's read it.
Swans are not white.
Some swans are not white, all swans are white.
So
Are those negations of each other?
Kind of.
Let's see. Let's visit our all yellow swan universe.
Okay.
All our swans are yellow. Okay. Are all swans white?
No.
No. So some swans are not white?
Yes.
Yes, it worked. All right, let's imagine that we live in a universe of all white swans. Are all swans white?
Yes.
Yes. So are some swans not white?
No.
No. So they're negations of each other. So here's our not alpha. This one is a negation of this. Either all swans are white or some swans are not white. Has to be one of those two.
Right. Has to be. It's not.
It always and forever has to either be alpha or not alpha. In other words, this right here is a tautology. It's something that's always true. Let's write it out really quick. So here's alpha. Alpha can either be true or false. Not alpha, then it has to be either false or true. So now let's look at alpha or not alpha. We're oring these two together. True or false is?
True.
True. False or true is?
True.
So this is always true. You always either have alpha or not alpha. It's always the case.
Always be true.
So when you have two negating statements, alpha and not alpha, then their disjunction is always true. It's always the case that it's either alpha or not alpha. The answer is 4 or the answer is not 4. All swans are white or some swans are not white.
For all swans are not white.
Well,
Maybe though.
let's try that one. You want to skip to this one? All swans are not white, right?
that's complete.
So either all swans are white or all swans are not white, right?
Yeah.
Right? So imagine we live in a universe where half our swans are white and half are black. Are all swans white?
No.
Then they're all not white.
Right.
No.
No, those are not contradictions of each other.
Okay.
So this is not the negation of this. I think we just skipped this one. So we either have all swans are white or not all swans are white.
True, yeah.
Yeah, there we go. That one's the negation. That's the one worded the simplest. Either all swans are white or not all swans are white. Either alpha or not alpha. It just turns out that this and this say the exact same thing. Just a
And it's flipped around. It's reworded.
yeah, it's worded different. And you'll learn how to do that rewording. Okay, so negation. The truth table for it is the simplest to write out, but it's the subtlest one to understand completely. All right. Example. State the negation of each of the following. All men in Georgia are at least 6 feet tall. What's the negation of that?
Not all men in Georgia are at least 6 feet tall.
Not all men in Georgia
That's
are at
so
least 6
simple,
feet tall. That's a simple way to say it. You could just put the not in front of there.
Yeah.
Let's try and say it a different way.
Some men in Georgia are not 6 feet.
All men in Georgia are at least 6 feet tall. Some men in Georgia are not
At least 6 feet.
at least 6 feet tall. Perfect. All students in France like geometry.
Some students in France do not like geometry.
Some students in France do not like geometry.
Or you could say,
Or
No,
not
no
all
students
students.
in
you
France.
could say
No
most.
students.
Okay, let's try the no students in France like geometry.
That's not true.
It's not going to work.
But the-
Let's say that half the students in France like geometry. Is it
Not
true that
true.
all students in France like geometry?
No.
No. So no students in France like geometry.
No.
No. It was
Some
just
do.
some. Some.
what about
So you're
most?
tempted to replace all with no's,
It's not.
and it's not going to work. It's going to be the first gotcha.
Right. What about most? Most.
Also
students in
not.
France-
No, that would be the negation of it.
All students in France like geometry, and the
Not
negation is
all.
most don't.
Most don't.
Most don't. What if most do?
Most.
It's not all, but it's not.
Oh, it's not most.
It's not least.
Okay.
All right. Let's move on to the next one. Every rectangle is a square.
Not every rectangle.
That's kind of
Not every rectangle is a square, or some rectangles are not squares.
so.
That's
It
not
could be also true. But right now it's the same, huh? So-
This is false.
It's false, but it's still stated.
Well,
You're saying the
So-
negation.
no, we're finding the negation. It doesn't matter. If
Yeah,
it's
we're
false or true.
just find the negation.
Doesn't matter, right?
So this is every rectangle is a square. The negation of that is some rectangles
are square.
Or not. All
are not squares. One of these two things has to be the case. Either every rectangle is a square, or some rectangles are not squares.
Right.
So this is the negation of this.
Right.
This one happens to be the true one. This one happens to be the false one. That's not what we're doing. We're just looking for the negation of each statement. Right?
Right.
Okay. Every circle has a center.
Some circles do not have a center.
Some circles do not have a center. For every pair of numbers A and B, A plus B is equal to B plus A.
Some pair of numbers, A and B, A plus B.
Not for
is
every
not
pair.
equal B plus A.
Perfect. For some pair of numbers A and B, A plus B is not equal to B plus A. Or there exists a pair of numbers A and B such that A plus B equals B plus A is false. There are some numbers A and B such that A plus B is not equal to B plus A. Say it a bunch of different ways.
Will there always be a negation to every statement?
Every statement has a negation.
Every
Because
statement,
not
every-
is a truth functional sentential connector. For any statement alpha you give me, I can just not it. There we go. We have a new statement.
Always.
Yeah.
For a statement.
For any statement alpha, not alpha, is still a statement.
Not all men play golf.
All right. Some men play golf.
No. Wait.
All men play
all
golf.
men do not play
Some men.
All men do not play golf.
That's not.
Or no men play golf. Let's write this one out. No men play golf.
You can't say all men do not because it's only
Either some men play golf
Or no men play.
or none of them do.
Not most men.
And sometimes you can phrase it as a question to yourself and it'll click in your head. Do some men play golf? No.
Yeah.
What does that mean?
Oh.
It means no men play golf. So just answer no to your question. Phrase it as a question, say no, and ask what does that mean?
Right.
Does every circle have a center? No. What does that mean? Some circles don't. Okay. There is at least one number x such that x plus 3 equals 7.
There is not at least one number.
There is not at least one number x such that x plus 3 equals 7.
Yeah, it's opposite, is it not?
Yeah,
There's no number X.
that's a better way to say it. There is no number x such that x plus 3 equals 7. Either there is some number that makes this true, or there's no number that makes this true. Cool. So that's practicing negating.
Can I ask you a question?
Go ahead.
On Friday, you asked us what we know.
Okay?
So if there's always a negation to something that is true or false, meaning you know it's true.
So let's say you know alpha.
Yeah.
You know that this is equal to true. That's what you know.
But there's
Then
always
you instantly know that not alpha is equal to false. And you instantly know that. If you know the sky is blue is true, then you instantly know the sky's not blue is false.
Okay, yeah.
Yep. No, I understood where you're going with it. Yep. Okay. Let's negate a conjunction now. Uh-oh. Today is Monday and the weather is cold.
Today is not Monday and the Well, oh wait, what are you trying to do? Make both statements false?
We want the negation.
Of both statements?
So here's alpha. This whole statement right here, this is now what I'm calling alpha. Here's my alpha. Now I want to know what is not alpha equal to.
Well, you can
Not
say
Monday, the weather is not cold.
well, you could even
Today
say
is not Monday and the weather is not cold. So let's pretend that today was a hot Monday.
yeah, you can say
All right. Today's a hot Monday. Let's pretend that that's the case.
Okay. So
All right.
that's all the-
Today is Monday and the weather is cool. Is that true?
No.
Oh, so it's not Monday and the weather is not cool.
That's true.
We just said, so what?
No, it's not true.
We went back in time to yesterday. So now it's Monday. And it's hot.
Yeah.
Okay. Today is Monday and the weather is cold.
False.
False. Oh, so today's not Monday and the weather is not cold.
So today is Monday and the weather's hot.
What's the negation?
Today is not Monday or the weather is not cold.
Or today is not Monday or the weather is not cold. Is the negation.
That's
Not and, or.
you switch out the conjunction for disjunction.
Correct. Or at least it seemed to work in that case.
Well, you said
Because either today is Monday and the weather's not cold, or it's the case that today's not Monday or the weather is not cold. One of those two has to be the case.
So then how is the opposite? So the opposite of a disjunction is a conjunction.
Well, maybe.
No, it has to be.
Well, maybe.
you can counter a conjunction with another conjunction. Oh,
No, you can't. That's what I'm
you
saying.
can't.
The opposite of conjunction is a disjunction. Means the opposite of conjunction is a disjunction.
Well, maybe. No, you're right. You're skipping ahead to not alpha is the same thing as alpha. Correct. So, we'll get there. Let's state the negation of this. All cats are black and all men are mortal.
Some cats are not black, or some men are not mortal.
Perfect. Some cats are not black, or some men are not mortal.
Can you also contradict a sentence by saying some cats? Oh yeah, some cats are white. Yeah. Oh, never mind.
Does it always switch between and or does it have to? Because some cats are not black and some men are not mortal.
So, if this statement is true, is the statement true?
No.
No.
No. So, we're setting up a statement that has to be true every time this one is false. It has to be false every time this one's true. So we said that some cats are not black, or some men are not mortal. Let's set up every possible universe and convince ourselves that one of these has to be true and one of these has to be false. Okay. So let's set up the universe where is it in fact the case that all cats are black and all men are mortal. Is this statement true?
In that universe.
Yes.
Yes.
If we're in the universe where every cat is black and every man is mortal, that is true. So now let's look at this statement. In that universe, would it be true that some cats are not black?
No.
Yes.
No.
Oh, not in that one. No.
Not in that universe. Would it be the case that some men are not mortal?
No.
No. So would it be the case that some cats are not black or some men are not mortal?
No.
No. If that's false and that's false, then that or that is still false. Right? Let's set up a different universe. Let's set up a universe where, let's set up our universe. All men are mortal, but not all cats are black. Right?
Yeah.
Right.
So this whole statement right here is
False.
false. Let's look at this statement. Is it true?
False.
Some cats are not black or some men are not mortal. Is that statement true?
False. False. False.
To our knowledge, there might be a man that's not mortal.
So we don't know for sure.
Donnie's holding a black marker or Donnie's holding a green marker.
True.
True.
You're not holding a green mark.
True.
I'm holding a black or I'm holding a green.
Oh, true.
True. Some cats are not black or some men are not mortal.
True.
True.
Because of the or. Because it's an or not an and. That's
Exactly.
an and to be false.
It's one or the other.
Which is why you have to switch.
So we set up a case where this one was false and it made this one true.
Right.
Let's think of another way that we could make this one false. We could be in a universe where all cats are black, but some men are immortal. Let's pretend that that's the case. We're in a universe where all cats are black, and I'm immortal. You with me?
Yeah.
Okay. Some cats are not black.
That's false.
False. Some men are not mortal.
That's also
True.
false.
That's true.
Oh,
True.
Sorry.
In our universe. So this whole statement becomes true.
Because it's norm.
So anytime you set up a scenario where this statement becomes false, this one becomes true. Anytime you set up a scenario where this statement becomes false, this one becomes true. Let's try and make this statement false. What is the only way we can make this statement false? We have to be in a universe where all cats are black and all men are mortal.
Make it false.
To make this whole statement false, the only way we can do it is we have to make this false and we have to make this false.
Right.
Right?
Right.
So, how do we make this false? Some cats are not black. All cats are black. How do we make this false?
All men are
Some
mortal.
men are not mortal. All men are mortal. This is a negation of this.
Right.
It's hard to do this at first, but you'll get to a point where this is something you can pretty easily do in your head. This is one of the reasons we have to run through logic. See how hard it is to do a basic logical analysis of simple sentences like this? We kind of have to give you the version of what's 6 times 6? 36. And you went through and you memorized that. You're no longer the kid who has to go 1, 2, 3, 4, 5, 6. Okay, that was 1 time. 7, 8, 9, 10, 11, 12. Okay, that was 2 times. Right now, that's how you're doing this right now. You're slowly thinking through it one little piece at a time. And I've got to blast you with tons of these statements. We got to get to the point where you just know it. So you notice with your homework, I'm going to give you just a ton of statements like this. And you're going to have to go through and do them all and do a logical analysis over and over again, a bunch of these statements. So, give you a lot of homework. There's a reason I'm giving you a lot of homework. It's because of how much you have to struggle at first to understand the statement logically. And I don't mean that in a pejorative way. Everyone always says, oh, be logical. As though they magically know logic. You don't magically know logic. You weren't endowed with this understanding. You have to learn it. It's a hard thing to do. And so, we're struggling to do it. All right, let's negate this one. Some rectangles are squares, and some triangles are equilateral.
All rectangles are squares and all triangles are equilateral.
Not quite.
Huh.
Some rectangles are squares. How do we negate that?
All rectangles are squares.
All rectangles.
No rectangles are squares. Or all rectangles are not squares. Either some rectangles are squares or no rectangles are squares.
Oh, you're right.
So I'm going to use the no verbiage. So it's going to be no rectangles or squares or no triangles or equilateral.
Well, you can say and too, right? Wait.
Nope.
Oh, no, you can't. No, you
We
can't.
have to set up a statement that in every possible universe, if our new statement's true, this one's false. And if this one's true, our new statement is false. That's the magic statement we're looking for. We're not just looking for a contrary statement.
Well,
We're not just going to go from all swans are white to some swans are black. Those are contrary. They can't both be true. That's not what we're talking about. It has to be the negation. You are coming up with a statement such that any way you can make this one false, our other statement has to be true. And any way you can make our other statement false, this one has to be true. They're the negations of each other. One has to be true, one has to be false.
and or does that.
And so you negate this piece or negate this piece.
Right.
When is alpha, here's another way to say it. When is alpha and beta false? How do I make this whole statement false? I either have alpha false or I have beta false. That's how this becomes false.
Or they can both be false, or they can both be true, right?
If they're both true, this statement's true. When is this false?
When they're both false or one false.
When they're both false.
When they're both false, makes it false. But what if just alpha's false?
It still makes it
It's
false.
still true.
What if just
Well,
It's not or. It's not or. It's
and.
and.
Okay.
this is an
It's
and?
not or. It's and.
We're looking at alpha and beta.
And, okay.
When is alpha and beta false?
When there's a false.
When alpha is false
Or beta.
or beta is false.
Right.
So the negation of alpha and beta is not alpha or not beta, which is what we're doing over and over again.
Right.
So some widgets are gadgets. This is our alpha. And no wiggles or waggles. This is our beta.
No widgets are wagging.
If we're going to do the negation of this, it's going to be not alpha or not beta. This is going to be the negation of this. So some widgets are gadgets. What's the negation of that?
No widgets are wagging.
No widgets are gadgets. That's our not alpha. Or
Some widgets are wagging.
some wiggles or waggles. Perfect. I think you're getting it. And so what we were showing is that not alpha and beta is logically equivalent to not alpha or not beta.
Right.
So now we'll quickly, rather than relying on intuition, we'll prove that real quick with the truth table. So we have alpha, we have beta. We're going to do not alpha. We're going to do not beta. We're going to do alpha and beta. We're going to do not alpha and beta. And then finally, we're going to do not alpha or not beta.
What does the negative sign mean?
That negative sign means not.
It's not a negative sign.
Yeah, it's supposed to be the drop down, sorry. And not that much of a drop down. I'll draw one good. This is what I'm trying to draw you. Okay. All right, so alpha and beta are any two statements. We have no clue which statements they are. They're any two statements. But there's only 4 possible combinations. We either have false, false, true, false, false, true, true, true. Right?
Yeah.
Right. So if alpha is false, not alpha is
True.
true. Here it's
True. No. Wait.
negating this. If alpha is true, not alpha is false. If alpha is false, not alpha is
False. True.
true.
Yeah.
Oh.
If alpha is true, not alpha is
False.
false. All right. Let's negate beta really quick. If beta is false, not beta is here it's
False. True.
true. Here it's
False.
false. Here it's
False. False.
false. We're just negating this column.
Yeah.
Okay. Conjunction. Now we're doing the conjunction of alpha and beta. We're conjoining these two columns. False and false is?
False.
True and false is?
False.
False and true is?
False.
True and true is?
True.
Perfect. Now here, we're doing the negation of alpha and beta. We're negating this column. Right?
Okay.
So let's negate it.
True.
Yeah?
True.
Yeah?
True.
Yeah,
False.
that wasn't so bad. Okay, now here we're ORing together, not alpha and not beta. So we're ORing these two columns together.
Okay.
True or true is?
True.
True, false or true is?
True.
True or false is?
True.
False or false is?
False.
And notice, no matter what alpha and beta are, these give the exact same thing.
Because they are the same thing.
And so they are what we call logically equivalent.
Right.
This is logically equivalent to
Distributed
this.
property.
Not alpha and beta is the same thing as not alpha or not beta.
So
Distributed property is like multiplying.
It's a lot like a distributed property, but notice it changes the and to an or.
would that only be with?
So the way we say that is when you distribute a not over a conjunction, it turns it into a disjunction.
Is that only with not alpha and not beta, or can it be with alpha and beta? So like alpha and beta is the same as alpha or beta?
No, those are not the same.
Those wouldn't be the same.
Alpha and beta is very different from alpha or beta.
So not alpha and not beta is the same as not alpha and not or not beta?
Not alpha and beta is the same as not alpha or not beta.
Not beta, yeah.
Yes.
But not alpha and beta is the same as alpha or beta is true. Okay, yeah.
Sometimes plugging in statements will help with clicking your intuition. I say, I'm a teacher and I'm a billionaire. Is that true?
No.
No, it's false. So either I'm not a teacher or I'm not a billionaire.
Okay.
I'm a teacher or I'm a billionaire.
Okay.
You don't know my financial situation.
Throw that.
All right. I could have been. All right. So we did and to or. Next is or to and. Negate each disjunction. I will study hard or I will fail. So you tell me, or maybe I tell you. I say, you will study hard or you will fail. You say, that's not true. What are you saying?
I won't study hard and I won't.
Yeah, you're saying I won't study hard and I still won't fail. Right?
So you won't study hard and.
So the negation of this is I will not study hard and I will not fail. Right?
Right. Yeah.
Next one. Some will work or all will starve.
All will not work. And
Not all. Not all will work.
No one will work.
Same as not all, but okay.
No one will work. Or
and
Some will start.
Or and.
Some will stop. Some.
no
Some
no
will
one will
start.
work. And
some will
some
start.
will
Yeah.
start. Some
No
will
one
not
will
start.
work and
And.
some will start.
And some will start?
And will not start. Some will not
No,
start.
will start. Yeah.
Wait, some
Wait.
will or will not
No,
start?
No. No one will work and
No one will work
some
and some
will
start.
thrive.
Start. No, start.
It's opposite.
And no one.
No one will work and some will not starve.
Yeah,
Will
some
not.
will not
Okay.
start.
Right? You're talking about a community of cannibals here. Okay. Next. Every triangle is isosceles or every triangle is right.
Not every triangle
Not every
is also
triangle.
isosceles. And not every triangle is isosceles.
Some triangles are one triangle.
No, we got it, didn't we?
You said it with the nodding each month, which works. He wants to use the sum language. Every triangle is isosceles. He's trying to say some triangles are not isosceles.
And some
And-
triangles are not right.
Some triangles are not right. Works perfect.
Also, would be some triangles is isosceles. Would that contradict every?
No.
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 Set up the universe.
Okay.
Let's say that some triangles are isosceles. Is every triangle isosceles?
No.
Maybe.
Oh.
We're just going somewhere.
Right. So it has to be not every triangle.
Right. Some of the students in this classroom are breathing. Is every student in this classroom breathing? That happened to be the case. It's still true that some are breathing.
Oh yeah.
All right. No roses are red, or some violets are blue.
Some roses
Some
are
roses
not red.
are red.
Not
I
red.
mean, not
and
Some
all
are-
no
are
violets are
red.
not blue.
What's the
No
opposite
violets are
of
blue.
no roses are red?
Some are.
Some are red.
Yeah.
Some roses are red.
Some roses are red. And
No violets.
no violets are blue. That works. Perfect. Okay. And now what are we showing? We're showing that not alpha or beta is logically equivalent to not alpha and not beta. So let's prove that one really quick. Switch that to an or, switch this to an or, switch this to an and. And that means we got to erase these columns. All right, so we're doing alpha or beta here. So false or false is?
False.
We're oring these two columns together.
Yeah.
So false or false is? False. True or false is?
True.
False or true?
True.
True or true?
True.
Perfect. Now this is a negation of this.
Okay.
So
true, false, false, false.
perfect. Now here we're doing the conjunction of these two.
Okay. True.
True and true is?
True.
False and true is?
False.
True and false is?
False.
False and false is?
False.
And
They're the same.
they're the same. So they're logically equivalent. No matter what alpha and beta are, these give you the same result every single time. If alpha is true and beta is true, still the case that not alpha or beta is the same thing as not alpha and not beta. If one's true, one's false, they're both false, etc. Okay. Another example of not versus never. So this is kind of like and but. So we use not in logic. We don't use the word never in logic. And notice that there's a difference between, when I say the sky is not blue, what am I saying?
Right now.
I'm saying the sky is blue is false. I'm saying that statement, the sky is blue, is false. If I say the sky is never blue, what am I saying? I'm saying the sky is blue is false. That's one thing I'm saying. But what else am I saying?
It's never.
Yeah, what do we mean by never?
You don't know.
We're somehow bringing in some sort of time dependency, somehow bringing physics into the situation.
Right, it's like
We're saying at this instant of time, but also at a future instant of time and a future instant of time
It's
after
like
that.
using but.
It's kind of like using but.
Okay.
This one we could make more precise, but it's now making it dependent upon physics.
Right.
Remember, you have logic, then math, then physics. You don't use physics to do your logic. You use logic to do your physics.
Right.
So we don't use the word never. We use the word not. Okay, proofs. When we try to convince someone of the validity of some statement, we say this is true because that is true. If they agree with that part of the statement, then they also agree that this necessarily follows. So I say this is true because that is true. If you agree with that, you're going to end up agreeing with this.
Right.
They'll accept that if they agree with three things. Two things. They agree that that is actually true. You say this is true because that is true. They might say no, that's false.
Right.
That's one way they could disagree
Right,
with
they
you.
might say that is true, but that's not. That's
Yeah.
not true.
So one way they disagree is they disagree with that part of it. Another way they might disagree is they might say, well, that may be true, but this doesn't necessarily fall from that.
Right.
So if you want to convince them of it, you got to convince them of the that. And you got to convince them that the this necessarily follows from the that. And they'll be convinced. So logic can be summarized as a study of the rules for making correct statements. Making true statements. Making statements that are always true. Putting them together and combining them. Proofs always consist of statements of the form, if so-and-so is true, then such and such must also be true. We're demonstrating that these things are true. That's what we do in a proof. I convince you of some statement's validity. I convince you that's always true. Let's look at some examples. Then I think it'll make more sense. If 3x equals 4, then x is equal to 4/3. True. How can I show you that? Divide both sides by 4. Divide both sides by 3. If you accept that as a valid rule, you see how this necessarily follows from that.
Right.
Next, if alpha is equal to 2 and beta is equal to 3, then a squared plus ab is equal to 10.
That's true.
It's true. Took you a little bit of algebra. I might have to walk you through some of the steps. But you see that if this is true, then this is necessarily true. That's how all our proofs are worded. All our proofs are worded in the if-then form. We're proving implications over and over again.
A squared is 4.
Yeah,
Plus
there's-
AB
there's-
is 5.
6.
Nine.
No.
Oh, it's not. It's supposed to be 8 times.
Okay. Yep. All right. So all mathematical proofs are of the form if alpha then beta. We call alpha the antecedent or the condition, and we call beta the conclusion. So I'm going to use that language over and over again. Antecedent, conclusion, or condition, conclusion. Usually I say antecedent. So we frame these proofs in an implication. So now let's look thoroughly at the logic of implications. So here's our next sentential connective, the implication. If alpha and beta are statements, then the statement alpha implies beta is called an implication. We also say there's a bunch of different ways we phrase alpha implies beta. We say this way, the same exact statement, tons of different ways in mathematics. Here's a few of them. We also say if alpha then beta. We say beta if alpha. We say alpha only if beta. We say alpha is a alpha is a sufficient condition for beta, or beta is a necessary condition for alpha. Those all say the same thing. We'll try and get used to all these different verbiages for saying the same thing. They're all saying alpha implies beta. We'll wrap our head around that. Notation, we write alpha implies beta as alpha arrow beta.
So is all this pretty much saying beta relies on alpha?
They all say that if alpha is true, beta must also be true. Beta necessarily follows from alpha. If alpha is true, then beta is true. Alpha being true implies beta is true. Alpha implies beta.
Beta doesn't imply alpha.
We're not saying beta implies alpha. We're saying alpha implies beta. We're saying if x equals 2, then 2x equals 4. Or a better example, if x equals 2 implies x squared is equal to 4. Notice this is true. The converse is not the case. If x squared equals 4, it is not the case that x equals 2. It could have been negative 2.
Right.
So this implies this. All right, so let's frame a bunch of these statements in the if alpha then beta form. So we need to identify our alpha and our beta in the statement and restate it as if alpha then beta. If I eat strawberries, I get hives.
Then I get hives.
If I eat strawberries, then I get hives. That's what this is saying. Next one. People who don't study mathematics don't have good sense.
If people don't study mathematics, they don't have good sense.
Then they don't have good sense. Right?
Is it saying if you don't have good sense, you don't study math, or if you don't study math, you don't have good sense?
Saying you don't study
If
math.
you don't have good sense, then you don't study mathematics.
Other way.
Saying if you don't study mathematics, you don't have
People
good
who
sense.
don't study mathematics don't have good sense.
As in,
So if you don't study mathematics,
you don't have good sense.
then you don't have good sense.
But
Yeah.
no, because you can not have good sense and still study mathematics.
That's not what it's asking.
Well, you don't know.
Here are all the people who don't have good sense. Here are all the people who don't study mathematics. If you don't study mathematics, then you don't have good sense.
Right.
If you do study mathematics, maybe you have good sense, maybe you don't. But if you don't study mathematics, you don't have good sense.
Yeah.
People who don't study mathematics don't have good sense.
Yeah, but it can't be if you don't have good sense, then you don't
Right.
study mathematics.
Right. It's if people don't.
If
Right.
people don't study mathematics,
They
they
don't
don't have
they
good
don't
sense.
have good sense.
Then they
So there can still be some people who study math who still don't have good sense.
Right.
But if you don't study math, you for sure don't have good sense. If you do study math, maybe, maybe not. Okay. Next one. The crops will be saved if we have rain this week.
If we have rain this week, then the crops will be saved.
Yeah? Anyone disagree with that?
Yeah.
Yeah.
Yeah, I disagree with that.
Yeah, you just switch it.
Oh, did you say if we have rain this week, then the crops will be saved?
Yeah. It says if we have rain this week, then the crops will be saved. Okay. Good. Next. It will rain tomorrow. It will rain tomorrow only if it gets cold.
If it gets cold, it will rain.
If it gets cold, it will rain
Then it
tomorrow.
will rain.
Right?
Then it will rain.
Or is it saying
Oh, no.
if it rains tomorrow, then it got cold?
No, it's not
Yeah,
saying-
yes, it is.
No, it's
It'll
not.
rain
It's
tomorrow.
saying
Because it's
only
saying
it'll only rain if it gets cold.
No, it's saying it will rain tomorrow. Wait, is it? Yeah,
It's saying,
It's
the only
saying it
reason
will
it
rain
will rain is
if it gets cold. Then that means that
So if it gets
relies
cold,
on
then it will rain.
if it gets cold.
Right?
So-
So
if it
is it
gets
saying
cold,
if
then
it gets
will
cold,
rain.
it will rain tomorrow?
Yeah, it's not.
Or is it saying if it ends up raining tomorrow, then it must have gotten cold?
No, it got cold. Yeah, huh?
It's gonna say,
It's
if
not
it rains, if it gets cold, it will rain.
It will
No.
rain tomorrow only if it gets cold. That's the only way it's possible
Okay.
to rain.
Okay. I'll convince you on this one. I found the magic sentence that makes it click in student's intuition. Here it is. True or false? There is oxygen if there is fire.
If there is fire, there's oxygen. Then there's.
Is this statement true?
No. Well, that we know of. Yeah.
Yeah, that's true.
Right.
There's not fire if there's oxygen.
Look around. If
Oh,
there's fire, there's
oxygen.
oxygen.
There is oxygen if there is fire.
That's
Oh
true.
no.
Did I say
not
that
true.
loud on? Sorry.
That's
Because
not
fire relies on oxygen.
So here's our alpha. Here's our beta. Is this saying alpha implies beta or beta implies alpha?
Beta implies alpha.
This one's saying beta implies alpha. This is saying if there's fire, then there must be oxygen.
Yeah.
Right, why don't you split beta and alpha?
Hold on. Now, let's replace if with only if. There is a fire only if there is oxygen.
That's also true.
That alpha implies beta.
So notice here, if we move the beta over here, so now we put beta on this side, right?
Okay.
Beta is there is fire. Alpha is there is oxygen.
Then that beta implies alpha.
So this is saying beta implies alpha. So these are both saying the same thing.
Right, but it's not beta implies alpha, it's alpha implies beta.
Well, alpha is there is oxygen.
Why? Why don't you just make it there's fire?
Okay, I could. It's just
We're
relabel
trying to
everything.
prove A equals, trying to prove
No.
alpha implies beta.
I'm trying to get you to see that both these sentences say the exact same thing.
Right.
That's all I'm trying to get you to do. So notice that replacing if with only if required you to swap sides that those were on. So down here, we were saying there is fire only if there is oxygen, means if there is fire, then there is oxygen.
Right.
It's saying this implies this.
Right.
Let's go back up to this one.
No, that's
If it
alpha
gets cold,
implies beta.
Then it will rain.
Forget that alpha and beta is just labeling the sides of the things.
Okay.
The point is it saying the first part implies the second part or the second part implies the first part? Here, we could see it was the first part implies the second part.
Right.
Up here. It will rain tomorrow only if it gets cold.
That's
It does not mean if it gets cold, it will rain tomorrow. It means if it rains tomorrow, it must have gotten cold.
It's only because it got
Right. Which is the exact same thing.
No.
You literally said it. You said it will rain tomorrow if it gets cold.
Because tomorrow it
Hold
As in,
on.
if it gets
Stop,
cold, then it
stop.
will rain tomorrow.
Let's label each of these.
Okay.
It will rain
I see
tomorrow.
what you're saying. 100%.
Do we want to call that one alpha or beta?
Alpha.
Alpha. It gets cold. We'll call that one
I
beta.
see what you're saying. I get it. What you're saying.
If I scribble out the word only, so we just have if. It will rain tomorrow if it gets cold.
That's not true.
That is saying, forget true or false. We're just asking what is it stating as the implication.
Right. Okay, I see.
This is saying beta implies alpha.
Right.
That's what we do when we just have if. If I get rid of that and now I say only if, I'm now saying alpha implies beta.
It will rain tomorrow only if it gets cold. You're saying if it will rain tomorrow, then it will get cold.
If it rains tomorrow, it's because it got cold.
Let's go down to the bottom sentence. There is fire. Should we call that alpha or beta?
Alpha.
Alpha. Okay, get rid of the only for a second. Beta. This says, if there's oxygen, then there's fire. Is that true?
No. Yes.
No.
So this one is saying beta implies, sorry, that's a
Oh,
B.
no.
No, that's definitely false. So this one is saying beta implies alpha when I scribble out the only, right? It's saying if there's oxygen, then there's fire, which is a false statement. There's tons of times that there's oxygen and there's not fire.
Right now.
Now I get rid of that only, or now I add the only. Now read it. There is fire only if there is oxygen.
That's true.
Now it's true.
Right.
So now it's saying alpha implies beta.
What do you call?
And this
Oh,
also
you're
has
saying
negation.
only
So
has-
this is.
Nothing
this
about
also works
negation.
with
I'm just telling you the difference between seeing if by itself and only if.
What do you call
Only.
them?
Nope.
I mean, like, these are
Just stick with that connection for a second. So if we get rid of only, and we put the if there, so alpha if beta means beta implies alpha.
Right.
Alpha only if beta means alpha implies beta.
You said the same thing.
This says alpha implies beta. If I scribble out the only, now it says beta implies alpha.
Okay.
Make sense?
Yeah.
One of the biggest gotchas in reading language. Now sometimes we want to say alpha implies beta and beta implies alpha. They both imply each other.
It doesn't work.
It happens all the time.
Does?
Yes. If not alpha or beta is equal to false, that implies not alpha and not beta is equal to false. Right? We showed that this is logically equivalent to this. Or maybe not equal to false, just say if it's true. Not alpha or beta implies not alpha and not beta. But similarly, if this is true, then this is true. So we do back and forth arrow like that for that. So this being true implies this is true, and this being true implies this is true. They imply each other. When two things imply each other, we often call them logically equivalent. And so it's very much the case that we're interested in statements, alpha and beta, where alpha implies beta and beta implies alpha. And so the way that we say that over and over again is we say alpha is true if and only if beta is true.
If and only.
If and only if. Remember, if we say alpha if beta, that means beta implies alpha.
Right.
And if we say alpha only if beta, that means alpha implies beta. So when we say alpha if and only if beta, then we're saying both of those can join together. We're saying alpha implies beta and beta implies alpha.
Right. Mm-hmm.
And we say that so stupid much in math that we write this as alpha if beta with two f's. And when you see the two f, that means if and only if. That's how we write it out loud. So alpha if and only if beta. So crucial that you understand how that only word completely changes how you think of the statement, the implication. All right. Put each of these in the form if alpha then beta. Oh, beta if alpha. Okay. So let's take each of these as beta if alpha.
I eat hives if I eat strawberries.
Let's just figure out let's just label each one of these alpha and beta so that it comes out this way.
Okay.
So which one of these is alpha?
I get
If
hives.
I eat strawberries.
Wait, we're trying to
If I
get
eat
it beta
strawberries.
if alpha?
If I eat strawberries, it's alpha.
Just try and phrase it this way. Maybe I'm confusing you. Try and state this as a beta if alpha statement.
I get hives if I eat strawberries.
I get hives if I eat strawberries.
So
So we're saying I eat strawberries, this was the alpha,
right.
and I get hives, this was the beta. That's what I'm saying to do. But I figure out the alpha and the beta. All right. People who don't study mathematics don't have good sense.
So we don't study mathematics, it's alpha.
No, that would be beta.
Well, people who
Try and phrase it this way.
People who don't have. Oh no.
if you don't have good sense, people
No,
don't.
that's not
People
true.
who don't have good sense don't study mathematics.
No, that's not true.
We're trying to say it this way. Beta if alpha.
People don't have.
People who don't study mathematics is alpha. Then it doesn't work with people who don't have good
Right.
sense that don't study mathematics.
People don't have good sense if they don't study mathematics. Not stating it that way. All right, let's do the next one. If we have rain this week, then the crops will be saved.
The crops will be saved if we have rain.
The crops will be saved if we have rain this week. It will rain tomorrow only if it gets cold.
No.
It will rain tomorrow. It's cold.
No,
It-
that's
it-
just- it will rain
it
tomorrow
get-
only
it-
if it gets cold.
If it gets cold, then
If it rains tomorrow, it's because it got cold.
no.
No.
It will get.
You're
cold
trying to
if it
remember
rains.
from
It
what
will
you
get
saw
cold.
last time rather than think about the logic of it.
It will get cold if it rains.
I swapped the order intentionally to confuse you.
If it rains tomorrow.
It will get cold.
What does
tomorrow.
only if mean?
It will get
If
B implies A.
Means alpha implies beta. If means beta implies alpha. Alpha if beta means beta implies alpha. Alpha only if beta means alpha implies beta. Right? So, it will rain tomorrow only if it gets cold. So, which ones are alpha, which ones are beta?
we're trying.
Alpha
So
is
the
if
second
it gets
one's
cold.
beta.
You got textbooks full of this stuff.
If it gets cold, it's beta.
No, if it gets
It gets
alpha.
cold is beta. So this is
Yes.
equivalent to it gets cold if it rains tomorrow.
So that's B in
It rains tomorrow only if it gets
That's what I
cold.
thought.
It's the
Which is
same
saying-
thing as it gets cold if it rains tomorrow.
So that is saying B if A. Already.
No, that's A. But A is B.
We need to rephrase this in this form. So which one's our antecedent? Here's our antecedent.
Yes.
It will rain tomorrow. So our antecedent we're putting here, our conclusion we're putting there.
Okay, so if it gets cold, no, it gets
cold
if it
if
rains tomorrow.
it rains tomorrow. It is the same thing as if it rains tomorrow, then it gets cold. Or if it rains, it will rain tomorrow only if it gets cold.
That's not saying.
Saying
it
I
gets
just said the
cold.
same thing a bunch of different ways.
Yeah.
Bunch of different ways to state an implication. And it's very easy for kids to get confused by this stuff when they first come across it. All right. If there is fire, then there is oxygen.
There is
State it
oxygen
this
if
way.
there is fire.
There's oxygen.
There is fire only if there's oxygen.
Nope.
Because
We're
that's
stating it this
saying
way.
B and A.
I want you to state it this way. Beta if
There is
alpha.
oxygen if there is fire.
If there's
Our
no,
conclusion is okay. Our conclusion is there is oxygen, correct? Okay.
Our conclusion is there's oxygen.
there's fire if there's oxygen.
Saying there's fire if there is oxygen.
Or
If there is fire, then there is oxygen. There being fire implies there's oxygen,
Right.
so
right? So now restate it as beta if alpha.
So what's alpha if there's fire?
You tell me.
I think it is. Which would mean there is oxygen if there's fire.
I want you to state a logically equivalent form of this statement. This way. So that there's an if in the middle of it. Rephrase this so that there's an if in the middle.
I did. There's
you have
oxygen if
only
there's
in
fire.
Because
Yeah.
There is
there's
oxygen if there's fire. No, just with an if, not with an only if.
There's oxygen.
I want
if
you to
there's
give me
fire.
statement
Yeah.
if statement, so it's logically equivalent to this.
Okay.
Okay. Let's do the next one. There is fire only if there is oxygen.
There's oxygen if there is fire.
No. Are you saying we imply the only if?
Or it is there's fire
That's already
if there's
good.
oxygen.
It's already good. Well, it's
No,
not
it's not
saying
good.
it.
There's an
It's
only
not
if in
saying-
there.
You
I
take
want you
the
to
only if
rephrase
out.
it so that there's statement if statement. Statement if statement.
There's
There's
fire,
oxygen
there's
if there's fire.
oxygen if there is fire. Again.
There is oxygen if there is fire. Said the exact same thing twice. So phrase it the same way twice. Good. All right. Conclusions. What can we conclude from the following statements? What can you conclude given the following statements? Okay. If Fred is on the team, he must go to bed early. So take that for granted. And A, so ignore this part, and Fred goes to bed early. What can you conclude?
He's on the team.
Or
Well-
he could not be. I mean,
No.
If Fred is on the team, he must go to bed early.
Then
And we know he went to bed early.
then
Then
Then Fred must be on the team?
Must be on the team.
No, maybe he caught a cold. Maybe he didn't make the team.
See?
But he's just feeling sick. He's just tired. He just went to bed early.
Still, okay. Right, it still doesn't mean he's not on the team, though.
But we can't conclude that he is on the team.
He's saying.
What can we conclude? If Fred is on the team, he must go to bed early.
Okay.
And we know that Fred went to bed early. Do we know that he's on the team?
No.
No.
That can't be true.
So we know that he went to bed early.
So all we know is he went to bed early. Okay, let's look at this one. Let's say we know if Fred's on the team, he must go to bed early. And we know that Fred does not go to bed early.
He must not be on the team.
Then he's not on the team.
Or he's not always on.
Well, we'll assume that the statement is true.
Well, he must, doesn't say he does.
Assuming.
If, like,
All right,
but
next.
right. In order for that to be absolutely true, you have to switch the word must.
We're not going to worry about that much. Get comfortable with the logic. All right. If a man is a postman, he has foot trouble. And we know that this man has perfect feet. What do we know?
Must not
He's
be.
not
Must
a
not be a
postman.
postman.
He's not a postman. On the other hand, if a man is a postman, he has foot trouble, and we know that this man has foot trouble.
But that doesn't apply.
He might have.
All we know is he has foot trouble. Maybe a postman, maybe not. Next. You will be given a ticket only if you are a sophomore. Gene was given a ticket.
George is a sophomore. We don't know that he was given a ticket.
Stick with A for a second.
Where did they?
You will be given a ticket only if you are a sophomore.
Gene was given a ticket.
Gene was given a ticket.
So that means that she received that which is, well,
Do we know she's a sophomore?
Yeah.
it's only saying that
Because only if you're a sophomore, you get a ticket. She was given a ticket.
and there's no other.
So no juniors can get tickets?
No, it's saying only if.
This just says if you're a sophomore, you get a ticket.
Only if you're a sophomore.
Yeah, only if you. So juniors, no tickets for them.
You're right the first time. Just want to see if I can confuse you.
Yeah.
Don't let yourself be confused. Yes, this is saying you get a ticket implies you're a sophomore. She got a ticket, that implies she's a sophomore. George is a sophomore.
We don't know.
Doesn't
the ticket.
mean you get the
It's
ticket.
not saying.
Doesn't mean he gets a
It's not
ticket.
saying if you're a sophomore, you will get a ticket.
Perfect.
It's saying you will.
The house will burn down if we don't get water, and we do get some water.
Doesn't prove
That
we got
implies
that
that
the house doesn't burn
and
down.
not burn down.
We will have, well,
That doesn't imply.
Actually, that
the
doesn't apply.
house-
it doesn't
It's
imply
not
that
that
we
it gets
just
water, the
got
house
a
might burn
cup
down
of water.
The house will burn down if we don't get water, and we did get some water.
But it
Did
doesn't
the
mean
house
that
burn
the
down?
house-
Honest.
Probably.
Maybe.
Yeah, we don't know, right? You might have just went and gotten yourself a glass of water to watch the show.
Yeah.
All right. On the other hand, the house will burn down if we don't get water, and you know that we don't get water.
That means
the
the
house
house did
burned
burn
down.
down.
The house for sure burned down in that case. Perfect. All right, no. Subtle distinction working towards vacuous truths. We haven't done the truth table for these yet. Maybe I'm overdoing this. Let's try. No. If something, then something is not the same thing as if it was the case, then it would be the case. If it was a case implies that we can somehow change something. It's like you're doing something in the universe, changing actual physicalities of the universe. So this says something different from this. Let's try and make that click in your head. If there are 100 husbands in America, then there is only one wife. Is saying something different from if it was the case that there were only 100 husbands in America, then it would be the case that there is only one wife.
No, that's not.
This implies that we can change something. This is talking about it as it is.
Right. So does that mean that we don't use if it was the case? We just use if? Is this like the but? And
So this is working towards what we call a vacuously true implication. We say an implication is vacuously true if the antecedent is always false. So if there are 100 husbands in America, then there is only one wife is a true statement.
No.
And that's going to bug you. I know. This statement is true. I'm telling you now, I'm not trying to confuse you.
how's
Now I'm
that?
going to try and work you through vacuously true. This statement right here is a false statement. This statement right here is a true statement.
How?
We're going to work up to it. This is talking about the universe as this is talking about there are 100 husbands in America. True or false?
We don't know.
No, we don't. It's false.
It's false. There are not 100 husbands in America right now. This is saying exactly. Right?
True.
So false. Okay.
But if it was the case that there were 100 husbands in America, that gives us time to go and change the system how it is.
Okay.
And we're messing with the system rather than just talking about the statement.
Okay.
It's going to be some. So vacuously true. So if the antecedent is false, then the implication is always vacuously true. False implies anything is always true. Sometimes you can prove it directly, sometimes you can prove it, oftentimes you can prove it directly. If you ever let me operate on a false antecedent, I can always prove anything is true. So if 1 equals 0, I can prove anything you want, as an example. Any false antecedent you give me, I can prove any ridiculous statement you want.
Right.
You have a ridiculous statement you want, or you want me to just prove that I'm the Pope? I'll do it for you. I'll prove it to you.
Right.
If 1 equals 0, I'm the Pope. I'll show you. You ready?
Yeah.
All right, let's assume 1's equal to 0.
Okay.
Add 1 to both sides. Then I get 2's equal to 1. Right?
Right.
The Pope and I are 2. But since 2's equal to 1, the Pope and I are 1. Therefore, I am the Pope.
I could also apply.
If you allow 1 to equal 0, then you must allow 2 to equal 1, right?
Right. And if you allow 2,
And the Pope and I are 2. Are we not?
Yeah.
Yeah, the Pope and I are 2. But since 2 is equal to 1, the Pope and I are 1. So I'm the Pope. So when you allow a false antecedent, you can prove anything is true. We call it vacuously true, but sometimes you can do an actual constructive proof like I just barely tried to do with me being the Pope. So now let's do the truth table for implication. It's going to bug you to no end. And students, they get to clicking their intuition, and then it goes away, and then it clicks again, then it goes away, and it comes and goes. The best thing to help my intuition for this is to remember that a statement that's not false is true, and a statement that's not true is false, which sounds obvious. But let's think about it. Okay, so we're going to make alpha, Donnie's holding a black marker. We're going to make beta, Donnie's holding a green marker. Okay. So let's have the first case. If I'm holding a black marker, then I'm holding a green marker. Is that true? Right now, if I'm holding a black marker, am I holding a green?
Yes.
Yes. You're trying to imagine, well, it's possible that in some future time I could have set down the green and then made the statement false.
Right.
We're not talking about this statement operate. This is the universe. Me holding this. All that exists. Like this. There's no such thing as time, space, anything else. There's just me and these markers. If I'm holding a black marker, then I'm holding a green. True. Okay. Next. If I'm holding a black marker, then I'm holding a green.
False.
Perfect. Next. If I'm holding a black marker, then I'm holding a green.
False.
That's false. Is it false that if I'm holding a black, I'm holding a green?
Yes. I'm not holding a black.
But if I am holding a black, am I holding a green?
Oh, yeah.
Yeah.
Is it false?
No.
No,
It's
it's
true.
not false. And if it's
Wait,
not
hold the
false,
green.
it's true.
Either way, you're holding green.
Right? So, if I was holding a black, if I'm holding a black, am I holding a green? Is that false? No, it's not false. And not false is the same thing as true. So it's true. Once again, if I'm holding a black marker, then I'm holding a green. Is it false that if I'm holding a black, I'm holding a green?
False.
No.
Yes.
Is it false?
No.
No. If it's not false, it's
True.
true. It's vacuously true. It can be very annoying.
It is no.
An implication, we call it vacuously true when the antecedent is false. So false implies anything is true. The statement, if I were a purple dragon, then finish it however you want. It's always true.
No.
Right.
But if, okay, I see.
It's called vacuously true. It's going to click in your intuition, then go away, then click, then go away. It's one that you're going to come to over and over again. This truth table right here. The converse. We call beta implies alpha the converse of alpha implies beta. Pretty straightforward?
Yes.
Okay. State the converse of each of the following implications and determine if it's true or false. So, if an animal is a man, then it is a human being. What's the converse?
If a human being is a man, wait, what? Wait,
If it is a human being, then it.
if a human being is a man, then it is an animal.
No.
No.
If it is a human being, then it is a man.
This is saying, if the converse is, if an animal is a human being, then it's a man.
Meaning, man is a
Being. So say that again.
If an animal is a human being, then it's a man.
Oh.
This is saying, so what's right in here is, if an animal is a man, then it's a human being. The converse is, if an animal is a human being, then it's a man.
Right. Okay.
Okay. True or false? If an animal is a man, then it's a human being.
False. False. Wait.
True.
Every man is a human being.
True. Yeah, true.
Okay. What about the converse? If it's a human being, is it a man?
No.
Yeah.
Could be
No.
a woman.
No.
Could have been a woman. All right, next one. Every man born in Indiana is an American citizen. True or false?
True.
True. Let's look at the converse.
If every man is born in Indiana, in America,
Every American
Every-
citizen.
every man born in America is an Indiana citizen. False. But does it mean that?
No, it's.
Every American citizen was born in Indiana.
I was trying to say it. Which is false.
What's his fault?
Which is false. The converse is every American citizen was born in Indiana. Everyone born in Indiana is an American citizen. Every American citizen is born in Indiana.
And every converse to a true is false.
No.
No?
No.
We'll get there.
There's no way to instantly know. If I know alpha implies beta is true, I can't instantly conclude whether or not beta implies alpha is true or false. Maybe true, maybe false.
So that's not one way you check to see if it's converse.
No. So if one statement is true, its converse may or may not be true. Okay, let's look at this one. If x minus y equals 3, then x is greater than y. Is that true?
Yeah.
If x minus y equals 3, then x is greater than y.
Yes, it's true. In order
Yes.
to subtract something, you
Yes.
don't have a negative. It has to be.
We took x, we took a bunch of stuff away from it, and we still had 3 left over. So x must have been bigger than y. Okay. On the other hand,
X is greater than y. If x is greater than y, then.
x minus y equals 3. And that's also true.
Oh, yeah.
No.
No, it's not true.
X could be 100, y could be 0.
Yeah.
Next. If plants are green, they must have sunshine. Is that true?
If they have sunshine, yes.
Well, let's start with is it true?
No.
Yes.
No.
We'll assume it's true. Chlorophyll needs sunshine.
Yeah, but a lot of plants don't.
There might be some exceptions out there. We'll assume it's true. If plants are green, then they must have sunshine. All right. What's
If
the
they have
converse?
sunshine, they must be green.
If they must have sunshine, then they are green.
So you keep the must with the.
Yes, this is saying must have sun. Look, it'd probably help if you identified what alpha is. So what exactly is the statement alpha? The statement is precisely plants are green. And the statement beta is precisely
Must have sunshine.
what must have sunshine. You need it as a statement. It's talking about something.
They must have
If we were to write this out precisely, the they here is substituting for plants. So if you were to write it precisely, it's plants must have sunshine. right?
Right.
But we have English, and so English lets us take little shortcuts, and it's supposed to be understood from the sentence what exactly is being said.
Right.
This is saying if a plant is green, then that plant must have sunshine.
Right. The plants must have sunshine if they're green.
Right. Which is,
Not true.
if a plant must have sunshine, then it's green, is false. Which would be the converse of that, right? All right, next one. If 2 plus 4 equals 5, then 4 plus 7 equals 10. True or false?
False. No, true. Excuse me. True.
True. Vacuously true. If the antecedent is false, the statement is always true.
Right.
Right?
Right. Even
If 2 plus 4 equals 5, I can prove anything you want.
Okay.
Because if 2 plus 4 is equal to 5, I'll prove I'm the Pope again. Well, 2 plus 4 is 6, so 6 is equal to 5. Subtract 5 from both, or subtract 4 from both sides, and we get 2 is equal to 1. The Pope and I are 2, therefore the Pope and I are 1, therefore I'm the Pope.
Yeah.
All right. Vacuously true.
Right, so just make it back into true again. If 4 plus 7 equals 10, then 2 plus 4
Yeah,
equals
so
5.
now the converse is if 4 plus 7 equals 10, then 2 plus 4 equals 5.
But
True.
you couldn't make the converse of it unless beta is false as well. Correct?
You can take the converse of any implication. Just
so
means
it's
swap
swap
it.
it.
Yeah. All right, contrapositive. Contrapositive of a statement, of an implication. Alpha implies beta. The contrapositive is not beta, implies not alpha.
Right.
The contrapositive is the same thing as the implication. So let's say alpha is I'm wearing shoes, beta is I'm wearing socks. If I'm wearing shoes, then I'm wearing socks.
Right.
The contrapositive of that is if I'm not wearing socks, then I must not be wearing shoes.
Okay.
So let's write this one out as a truth table. We have alpha, beta. We're going to have not alpha. We're going to have not beta. We're going to have alpha implies beta. And then we're going to have not beta implies not alpha. And say that they're the same. All right. So for alpha and beta, how many possible combinations do we have?
True.
We have true,
false,
false,
true, true, false, true, false.
Perfect. Now we're negating alpha. Tell it to be quick.
True. I mean false. True. True. False. Again. True. True.
Right, we're just negating these.
Yeah.
All right, next.
True. False. False. True.
Perfect. Now alpha implies beta. True implies false is
True. No.
false. Let's set it up. If I'm holding a black marker, then I'm holding a green marker.
False.
False. I made the antecedent true, but the conclusion false. All right, true implies true is
True.
true. False implies true is true. Vacuously true. False implies false is true. Vacuously true. All right, now let's look at not beta implies not alpha. True implies false is false.
False.
True implies false is false.
Right.
Yeah.
If I'm holding a green marker, or sorry, if I'm holding a black marker, then I'm holding a green marker. Doesn't work. All right, next. False implies false is
True.
true. Vacuously true. False implies true is
True.
true implies true is. And look at that, they give the exact same thing. So the contrapositive, logically equivalent to the implication. Alpha implies beta is the same thing as not beta implies not alpha. Sometimes you're often told to show alpha implies beta in your proof. It's often easier to think about that as, maybe I'll just prove not beta implies not alpha instead.
That's how you do that.
Yeah, it's a common proof technique. If you can't figure out how to do it as the implication, you think about its converse and try to prove its converse instead, since they're logically equivalent. So, kind of proof technique. All right, state the converse and the contrapositive of each of these. All right. Let me look ahead real quick. Maybe we'll skip that and go straight to this. All right, so we've already done a bit with this one, the if and only if. If and only if are the logical equivalent. So, if and only if. Observe that alpha if beta is the same thing as beta implies alpha. Alpha if beta means that beta implies alpha. Right?
No.
Alpha
Yes.
if beta means beta implies alpha.
Yes.
And that alpha only if beta is the same thing as alpha implies beta.
Right.
So, alpha if beta is beta implies alpha. Alpha only if beta is alpha implies beta. Then, alpha if and only if beta is the same thing as alpha implies beta and beta implies alpha. Since alpha if and only if beta is so frequently used, we say alpha if and only if beta with two f's like that. And this is what we mean by logical equivalence now. So our next logical operator. Logical equivalence and the last logical operator we care about. We call the two statements alpha and beta logically equivalent, provided that alpha if and only if beta. So if alpha implies beta and beta implies alpha, we call them logically equivalent. We also call alpha if and only if beta a biconditional or an equivalence. Notation, we write alpha if and only if beta as this back and forth arrow. Saying alpha implies beta and beta implies alpha. All right, so let's do our last operator. Alpha, beta, alpha implies beta, beta implies alpha, alpha. And then finally, alpha if and only if beta. All right, so for alpha and beta, what are all the possible combinations we can have? True, 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 false, false, true, false, false. Okay. True implies true is?
True.
True implies false is? False. False implies true is? False implies false is? Good. True implies true is? False implies true is? True. False implies true is vacuously true. If the antecedent's false,
Anything can be true.
Anything.
then the conclusion's always true. True implies false is? False. False implies false is? True. Okay. Now, alpha if and only if beta is a conjunction of these two things. It's saying alpha implies beta and beta implies alpha. Right? So we're doing the conjunction of these two. False and true is?
False.
True and false is?
True.
False.
It says
And.
conjunction, not subject.
Conjunction. Oh, disjunction, I mean.
Not disjunction.
And true is?
True.
Perfect.
There can never be a false factor in it for it to be true.
With the conjunction.
With the conjunction.
With the conjunction. Alpha and beta is true if and only if both alpha and beta are true. All right. So now notice the pattern here. When was alpha logically equivalent to beta? So we got true, false, false, true. When is alpha logically equivalent to beta? When alpha and beta have the same values. If alpha and beta are both true, they're logically equivalent. If they have different values, they're not logically equivalent. If they have the same value, they're logically equivalent. That's why we also call it a logical equivalence. It means alpha and beta have the same truth value. They were either both true or they were both false. That's the only way you get alpha implies beta and beta implies alpha. Is if they're both true or they're both false. Or in other words, they're equivalent. They're logically equivalent. That's why we call it an equivalence. Okay, so here's the different operators that we've talked about. We've talked about not, and, or implies, and equivalence. And this is the order of their precedence. First you do your nots, then you do your ands, then you do your ors, then you do your implies, then you do your
In a true
equivalence.
table, you're saying?
Just when you're reading it, it's understood. The same way that if I say, what is negative 6 times 7 plus 3 equal?
Oh, it's like pen box, is what you're saying.
Kind of, yeah. So you know, oh, negative 6 times 7 is negative 42. So you apply the negative to the 6 first, so that's negative 6. Now multiply it by 7, so it's negative 42 plus the 3, right?
39.
Yeah.
Right.
So that's the order of precedence, and we didn't have to put parentheses everywhere. So similarly, you'll kind of just get used to this with time. But if I were to show you that alpha implies beta is equivalent to not beta implies not alpha, that's the same thing as putting in all the parentheses, alpha implies beta, is logically equivalent to parentheses, not beta implies not alpha.
Okay.
So that's putting in all the parentheses, so that you see explicitly when you do which operator. So most of the time it will be pretty intuitive. Between the ands and the ors is when it's not so intuitive. So alpha or beta and not alpha is the same thing as alpha or beta and not alpha. You're just putting in all the parentheses. So you'll get used to that precedence as you see this notation more and more. But that's the way it works. Okay, so quick review of propositional logic. What is a proposition?
Statement.
Oh, sorry, we're doing statement. Statement. What's a statement?
Set. Statement.
A statement
True or
is
false,
a
but not
sentence
both.
True or false, but not both. Perfect. And then we have these 5 logical operators. This one is
No.
not. This one is.
And
This is.
or implies.
Implies.
Only.
Equivalent.
If and only if or equivalent. Perfect. We proved a couple theorems. We proved that not alpha and beta is the same thing as not alpha or not beta. So that's now a theorem of logic. We proved that not alpha or beta is the same thing as not alpha and not beta. So that's now a theorem of logic. And we proved that alpha implies beta is the same thing as not beta implies not alpha. So that's now a theorem of logic. These are now theorems that we can use in every field of study.
So are these
Biology, physics,
Are
math.
these one of the threes that Lucid got? Whatever it is. Whatever it is.
You're saying Aristotle?
No. You said at the very beginning you said he had 5 postulates.
Oh, Euclid. No, these are theorems of logic. These are not postulates of geometry. So far, this has nothing to do with geometry. It's just pure logic. It's Aristotle that developed logic. Okay. So remember that x plus 2 equals 5 was not a statement
Right.
or proposition.
Because it depended on that.
Because it depends on x for its truth or false value. So it's going to be what we call a predicate, which is what we will start with next time. We will do a quick class through of predicate logic. Now, so that's it for lecture, and then we'll talk homework for a second. Stop the recording.